All right, y'all. So today we're going to classify mixtures a little bit more. So far we've looked at heterogeneous and homogeneous, but that's not even as simple as we can get when we talk about mixtures. So as we continue to classify these things, the details and the differences are going to get a little bit more specific. So in our notes, we're under the organization of matter, and we are going to, I just want to start with a couple of reminders about mixtures, and then we'll get going in terms of solutions, okay? So at this point, right, we're understanding these basics, and when we hear the word mixture, we often have vibes of like combinations, pieces coming together, different stuff, which is all true. And so again, our chemistry definition of a mixture is a combination of two or more pure substances in which each pure substance retains its individual chemical properties, meaning that they are not forming something new. There's, when you mix things together and then you're able to separate them, they still have their own identities. And so, as we think about this, let's think about the following. Okay, so we've been tossing around this word pure substance, and I just want to make sure that we actually know what it means. A pure substance is an element or a group of elements that are chemically combined. So as you mix those pure substances together, that's how you're getting your mixture. But the pure substance itself, let's think about that. Okay, so hopefully you picked Kool-Aid for that question. Kool-Aid is not a pure substance. There's no chemical involvement when you are dissolving that Kool-Aid mixture into your water. So let's break it down, these mixtures, into their little pieces. So first up, we've got solutions. Okay, so again, in our notes, here's what we're talking about. So when we talk about solutions, think about things like sugar water, salt water, or even maybe just pink water or light yellow water, for example. Often, though, however, people assume that solutions can only be liquids, but this is not the case. Solutions can be a solid, liquid, or a gas. Let's talk about some of the properties that are going to make solutions different from other types of mixtures. They are homogeneous, right? So the different particles are going to be uniform throughout. So if we look at something like this, you might see air bubbles in there because I just poured this from the tap, but I don't see pieces in this, okay? There's only one phase of matter at a time. So while a solution could be a solid, liquid, or gas, the solution itself has to be the same. So if you put solids in there, the liquid, now you've got different phases of matter, not a solution, okay? The particles do not settle out, meaning if I leave this this flask of water out, it's still going to be a flask of water when I come back to it later. There's not going to randomly be hydrogen and oxygen or minerals separating out, things like that, okay? The other thing to keep in mind is that if I ran water through like filter paper or a sieve or anything like that, on the other side, it's still going to be water, okay? So we say that they cannot be separated. That's one of the properties of a solution. They cannot be separated by physical means. The other thing to keep in mind is that your solutions are going to be clear. Now, keep in mind the word clear and colorless are not the same. Okay, so a solution could be yellow and clear, and that's fine. Okay, so clear. The other thing that we can do with a solution is that when we use the Tyndall effect, which you just learned about, for a solution, that light is going to pass right through. Okay, so if I were to hold up a flashlight to this water, it would go right through. Okay, this is actually a solution of water and isopropyl alcohol. Okay, you don't know that. It looks like water to you. Okay, but the light would just pass right through, and we call that a negative Tyndall effect. So let's think about the following. Okay, so solutions are actually made up of two components. We call it the solute and the solvent. The solute, or solutes, if you have multiple components. The solutes are what get dissolved. So if you think about making crystal light, that crystal light packet is what gets dissolved. Then the solvent is what does the dissolving. Okay, so if you're, again, in that crystal light example, water would be your solvent. and the crystallite would be your solute. Okay, so go ahead and think about the following question. All right, it's always good to have examples. So if you think about the atmosphere, that's going to be a mixture of nitrogen and oxygen. So that's a gas example of a solution. Lemonade, iced tea, isopropyl alcohol and water, right? Those are all examples of liquid-liquid solutions. Yesterday or the other day, I was talking about cymbals, like in a band, right? So cymbals are a combination of brass or steel, which is steel is like iron and carbon, which makes up the Liberty Bell. Those are examples of solid solutions. Okay, so now let's talk about suspensions. So suspensions are the easiest one to deal with, to be perfectly honest. They are heterogeneous mixtures, meaning that you have the ability to see the pieces, okay? You look at that and you're like, boom, it's a suspension, okay? So it has larger particles involved. Typically, they are things that have to be shaken to distribute throughout. So anything that you've ever used that says shake before using, that's going to be a suspension, because that means that the layers over time were able to separate out as it was being made. They tend to have larger size particles that you can see, right? You look at it and you can see it, which also means that suspensions can be filtered. So if you think back to the lab, right, we had the charcoal in the water. If you were to run that charcoal in water through some filter paper, the charcoal would stay on one side and the water would go through. And again, thinking back to our salad dressing, right, as you look at that, you can definitely see there's stuff in there, okay? You can see all that nice flavoring that gives Italian dressing its pizzazz, right? So all of that flavoring in there could be filtered out. That's how I know it's a suspension. So I want you to think about the following question and give me some reasonings why. Okay, yeah, so we don't use the Tyndall effect on suspensions. We don't need to. You look at it, you can tell it's a suspension. The other reason, again, think back to that charcoal in the water. When you first received the sample, it looked black and uniform in appearance, okay? Shine the light through there, you're probably going to get a positive Tyndall effect that it will glow. Leave that solution out for a while, well, now you're going to have a separation, okay? The charcoal probably sunk to the bottom, or some of it was floating on top, and then you had water that when you shine the light through it, well, now it's a negative Tyndall effect. So we don't typically tend to use the Tyndall effect for suspensions. Again, that's just because you can tell it's a suspension right off the bat. All right, and now let's talk about colloids, okay? So colloids are our kind of like our middle child of the mixture category. They don't have large particles, but they don't have teeny tiny particles like solutions either. They have like slightly small. Okay, so colloids are, like I said, they're that like in between. They're between a solution and a suspension. There are different particle types that are not necessarily evenly distributed, but are small enough that when I look at it, it's not settling out. Okay, so again, think back into the lab. We had milk as our colloid in the lab. Okay, they're typically cloudy or opaque in appearance. This is due to the slightly larger particle size as compared to a solution, right? Solutions had teeny tiny particles that you couldn't see. Slightly larger particles are causing that sort of cloudy or opaque look to them, okay? So if we think about like fat droplets in water, well, the light's not going to pass through that colloid, but instead it's going to have that glowish thing happening. We also cannot separate colloids by physical means. If I were to run milk through filter paper, on the other side of that filter paper would still be milk, okay? And so we don't say that they are easily separated like a suspension would be, okay? It's gonna, same thing over there. So my friends who have done driver's ed, there's always like one piece of advice they give you when they talk about fog. So think about that for a second. They always tell you not to use your high beams. And the reason for that is fog is an example of a colloid. There are slightly larger particles, right? The actual water that makes those clouds visible. The reason we can see fog, right, is those slightly larger particles in that cloud from the water. So when you turn on your high beams, whoop, into a cloud, now all those light beams from your headlights are bouncing around inside that cloud, bouncing off the water particles, and it makes it glow. And so if you use your high beams, during fog, then it sort of creates this like light shield of glowing light in front of you that you cannot see through. Okay, and so fog, the whole reason we have that safety rule not to use our high beams is because it's a colloid. So again, it's those larger particles that are getting in the way of those light beams, causing it to sort of bounce around, which is going to get into physics, but that's what's happening there. So let's think about this next question and take your time when you answer it. Okay, so colloids, solutions, suspensions, that's how we are going to define our mixtures. And there are lots of different ways that we can do this, but keep in mind those main properties that we discussed in this video to help you classify.